Thanks for the invitation. Yes, I'd like to tell you a bit about this area of lattice-based cryptography. Today is a lot about learning, so we heard Leslie Valiant's talk, Ron Raz's talk about learning, and this will also be a bit about learning. I'll also talk about applications, recent stuff, applications to machine learning, just because these days, I guess you have to do machine learning. Everyone must do some kind of deep learning or machine learning. So I'll tell you a bit about that. So that's more recent stuff, but most of the talk will be about learning with errors. So let's get going. So the story starts back in the mid-90s when Peter Shor discovered that quantum computers can factor numbers. They can factor integers into prime factors. So this was in the mid-90s, and this was a big crisis, and still is a crisis in cryptography because all the cryptographic protocols we use, almost all of them, are based on assumptions like that factoring numbers is hard, and Adi Shamir is here to blame for that, and the other assumptions like discrete log or elliptic curve crypto, they're all based on things that quantum computers can efficiently solve. And that's a problem because we want to use crypto, and now many people are worried that soon we won't have any ways to encrypt information or sign documents, HTTPS, banks, et cetera, et cetera. So obviously cryptography is very important nowadays for economy and something we really want to have. So now there's kind of this race of who's the first to build a quantum computer. You must have heard about this. It's all over the news. I'm not sure what took so long because this could have happened already 20 years ago, but only recently that kind of arms race actually picked up. So this is a new story about IBM and of course Google and Microsoft. Everyone is trying to build a quantum computer. When would it actually be built? We don't know. Probably not 50 years. I'm hoping for less. Depends on who you ask. If you ask Gil Kala, he might tell you never. Some will tell you in a few years. But they do make impressive progress. Like there was recent quantum supremacy claim from Google. It's not yet there. Obviously, they can't factor big numbers yet, but it's getting there. And they're making very nice progress. There's even a story recently that the White House, there's lots of money being poured into it. I hear even here in Israel, they're pouring lots of money into it, to building quantum computers. It's because of this arms race, with the Chinese be first, the Americans be first, and there's a story here saying that Trump also wants to put, did put $1 billion on the quantum technology research, and they really want to scare you, so they tell you that experts believe that quantum computing will soon be able to crack classical encryption, and the moment will be possible, it will be referred to as Q-Day, like the day quantum computers can break encryption, the Q-Day. And to make it worse, they show you two Trumps. So you're really worried, right? You're really very concerned about this. Say again? On more than 1 billion, yeah. Yeah, I guess 1 billion is not that much in the scale of, yeah, okay. But hopefully they'll get there soon, either Chinese or the Americans. The solution or the answer to that came a few years later, 2 years later, with a seminal paper by Mikhail Shaita and Cynthia Dwork, and they had this ingenious idea that maybe you should use something completely different for crypto. Let's not use factoring or discrete log. Let's use something completely different, and then we'll use those high-dimensional objects called lattices. This is a two-dimensional lattice, but what they were suggesting is somehow to use them, or more precisely to use the hard computational problems associated with them, use them to build cryptography. Okay, so that was revolutionary idea. Prior to their work, lattices have been used in crypto, but mainly to break encryption. They were the first to say, let's actually use that to encrypt, to create crypto. So this was 96. So what are those lattices? This is in Hebrew it works better, right? It's a lattice of lattices. I had trouble with that. I still have trouble with that, right? So this is another two-dimensional lattice. So it's two-dimensional lattice. It's periodic structure of points, a set of points in high-dimensional space. Typically, for cryptography, it will be maybe in a few hundreds of dimensions, not in 2 dimensions. You'll need a few hundreds of dimensions to make the computational problems hard. So what are the computational problems? We'll get to that in a minute, but more precisely, those lattices are mathematically defined as, if you wish, discrete subgroups of Rn, or if you want more concretely, it's a lot like the linear span of n vectors, except you take only the integer combinations. So let me just define it. This is probably the only definitions I'll need in this talk. So you take n linearly independent vectors, v1 up to vn, and you take all their integer linear combinations. So it's a set of all vectors a1, v1, plus a2, v2, and so on up to a and vn. But a's have to be integer. Okay? So here's a picture. I took v1, v2, and then I take all their integer combinations. So there's 2 times v1, v1 plus v2, and so on. But it kind of goes to infinity in all directions. Okay. And the problems on this, geometrical problems on this, are all hard. So I won't make it very precise, but things like, I give you the basis, I give you v1 up to vn. Can you find a short vector? Non-zero. Of course, 0 is always there, but can you find a short vector? That seems like an exceedingly hard problem. Why is it hard? It's because the basis I would give you is usually not made of short vectors. Usually I would give you a basis made of very long vectors, and you would have to find the right combination to get short vector out of those long vectors. Right? So just like a linear subspace has lots of bases, same here, you can take very long vectors, v1, v2 up to vn, and trying to find the right combinations, it's really hard. There are exponentially many possible ways to combine the vectors, and we just don't know how to do that efficiently. This seems a very hard problem. I'll get back to it in a minute. But the idea, again, of I-timed work was to use those hard computational problems to create, to build cryptographic protocols. And more precisely, here was the idea. This is a very basic idea. It's not how it's done today. It's not how you actually encrypt. But the idea is still there. The same idea, I would say, is still there. And what they were saying is something very simple. So here's like the one-line summary of lattice-based encryption. Of course, I'm hiding lots of details. But the idea was that if you want to encrypt a message, so imagine you associate somehow each lattice point here to a possible message. So maybe this is, maybe this is yes, this is no, this is maybe. So each point somehow is maybe a message. And maybe I want to send this point here. Maybe this point says yes, and I want to send you yes. All I have to do is just move the point by a little bit, and that's my encryption. So again, I want to send you this message. What I would do, I would move this point by a little bit, and that's going to be my encryption. What's the idea? The idea is that because we're in a high-dimensional space, it's not two-dimensional, it's like 100-dimensional. Going back from here, going back to here is actually really hard because there are exponentially many directions. It looks, on the picture, it looks very easy. I just moved a few millimeters down, but going back in high dimension is very hard. I don't know which direction to go. So an eavesdropper that just gets this encryption here will not figure out that the message was actually the one here that encodes a yes. But those who have the key, those who hold the key, can round the point back to the original point. They can figure out what the message was. And that's because the key here, or the private key, I should say, is a very good basis, like an orthogonal basis, almost orthogonal basis, allows me to decode or to round back to the nearest point. But the eavesdropper doesn't have that good basis. The eavesdropper just kind of sees this whole lattice, but doesn't see the geometry, doesn't see the microstructure, doesn't see the actual points next to each other. It knows the basis, it knows a bad basis, but it doesn't have this nice and good basis. So basically this interplay between good basis that serves as the private key and a bad basis that serves as a public key is this idea of Cynthia Dvorak and Miklos Shaitan. So we'll get back to see it more concretely. You'll see later how to encrypt nowadays. It's done a bit differently, but the idea is still there of how this noise or this movement affects things. I should have said the way you move the point is random. You don't want to move in any particular direction. You just move it randomly. And noise or random noise plays an important role in this whole area. So Ran Raz was talking about parity without noise. here noise is very important for the hardness of those problems. Okay. So we'll get back to encryption in a minute. I'll show you a little demonstration. Yes. No, so you can actually send as many as you wish. You can reuse that key. It's semantically secure. So yeah, so I was oversimplifying a bit. Yeah, so you're right. If I keep sending the same point, I would see that all the points cluster in the same area. So the way you want to think of it is maybe I'm not going to give you all the details here because there's a much more elegant way of doing it. But the way maybe you want to do it is that many points correspond to yes. To yes. Maybe there'll be a hash function that this is yes, also this is yes. So I don't have to send the same point twice. There are other ways of doing it. Yeah. Yeah, but the idea can be made semantically secure. Yeah, so that's true. Thanks. Yeah. Okay. So the reason this was interesting and still is very interesting, or generally lattice-based crypto, the reason we care about it is because it seems secure. The best known attacks require exponential time, exponential in dimension. That's why I said dimension should be a few hundreds, because the best attacks run in time exponential. But the reason it's especially interesting is because there's nothing better known quantumly. Okay, so if you think of factoring or deeply secure crypto, discrete log, those things are quantumly broken. Classically, they're hard. Actually, there are sub-exponential time algorithms for factoring, right, like number field sieve, but quantumly they're totally broken. But here, in lattice-based crypto, we don't know of any quantum attack, and that's really the million-dollar question here: is there a more efficient quantum attack on lattice problems? And that's something that was on people's mind for I guess over 20 years now. Everyone wants to be the next Shor. Everyone wants to find the next big quantum algorithm, right? So, we're all trying to build quantum computers, but there aren't that many known quantum algorithms. So we can factor numbers, take discrete log. There are a few other cool things you can do, like Pell's equation. But there aren't that many quantum algorithms, and this is an especially important problem because this might be the future of cryptography, and we really want to know if there is a more efficient quantum algorithm for those problems. It's been around for a long time, and everyone wants to be the next Shor, as I was saying. Even Shor wants to be the next Shor. Even Shor tried to find quantum algorithms for lattice problems. So many people, I think... It's hard to prove impossibility in this area. Those problems are not... And even NP-complete would not, strictly speaking, would not be an impossibility result. But those problems are not NP-complete, and it's really based on belief. Just like factoring, we think factoring is hard, but some people think, not everyone thinks factoring is hard. We hope it's hard, at least classically. Quantumly, we know it's not hard. So it's all a question of belief and how did we try hard enough. And I think people try here. People also still trying. I'll say more about what's known about this, attempts to solve lattice problems quantumly. I should say about once or twice a year, I would wake up with that email saying, here's a claimed attempt, or someone claims that they can solve lattice problems using quantum algorithms. And so far, everything was false. But there was a very nice attempts over the years. I can remember these two very nice attempts, like highly non-trivial algorithms, new ideas, but they all failed. Many failed for a similar reason. Many attempts failed for similar reasons. But still, once in a while, there's a nice idea. But yeah. Okay, so to be precise, so Nadia's question was: is there anything proven, any improvement at all? You can do things using like Grover's algorithm. You can get slight improvements. And actually, I think the state of the art. Okay, don't quote me on this, but I don't think you can do anything currently, even with Grover. I'm not sure but that improvement you can get is very small. It's a constant exponent. It's quadratic at most quadratic. So. I'm ignoring it for the purposes of this talk. I think if you allow heuristics, yeah, you can get slight improvements using Grover's. So I think this is a great question, and I won't answer the question here. I can tell you that we tried. What we realized at some point is that Gaussian distributions, the Fourier transform, those ideas are very useful. They interact very nicely with lattices, and many of the attempts we have, or people had, use those ideas, try to use Gaussian distributions, use Fourier transforms. So this is something we did with Daniele Michancio in 2003. What we also realized later is that actually you can use these ideas, and you can use these ideas to come up with an algorithm. So you can come up with a quantum algorithm that solves lattice problems. But there was one caveat, and the caveat was that there's one small missing part. So it doesn't quite work. There's one small part that was missing from the algorithm, and here's what was missing. So it is a problem of kind of detecting what I would call like noisy periodicity. So what is the problem? It's a problem where you get a list of samples. Okay? You get a list of points. Those points are taken from some distribution, and you're supposed to find the pattern in those points. So let me give you an example. Here is a video showing this. So there are those points that keep showing up, and you're supposed to tell if there's some pattern in the points. And I think you start, probably at this point, you realize there is some pattern. So what you know is that those points are going to align on those lines. That they form this line pattern, and your goal is to identify this pattern. So it's some kind of learning problem. You get those samples, you're trying to learn where the pattern is, what this periodic pattern is. And I think that's an important slide. I mean, I want you to realize this maybe looks easy because you can easily see that, but the problem is that usually it's much denser. I mean, here what I showed you is only 1, 2, 3, 4, 5, 6, maybe eight of those lines. But actually, the problem involves many more of those periods, like maybe 2 to the power 100. So it's much denser. It really seems extremely hard to find where the period is. So here again, I gave you lots of points. You really see the pattern, but as it becomes denser, I hope you'll believe me. It will be very hard to see that pattern. You won't get so many points on the same line because there are so many lines. They're so dense together. So this was where we got stuck, because we knew if we can solve this, if given points we can figure out the period, we would be done with lattice problems. Okay? And this is something we still don't know how to do in better than exponential time. So this is, let me give you another example. This is in 2 dimensions. We could actually, 2 dimensions, and you don't have to go to high dimension. You can do it in 2 dimensions, that's enough. You solve lattice problems in all dimensions. You don't have to think, this is really the problem. In fact, you can do it in 1 dimension. There's no need to go to 2 dimensions. So this is actually one way to think of it. Here's the same thing, just in 1 dimension. You get points. The points come from some periodic distribution, and you're trying to figure out what the period is. Again, here it's very small. The period is 5. You can immediately see that, but imagine the period is like 2 to the power 100. How would we ever figure it out? If you can do it in better than exponential time, time is in the log of number of periods, that would be fantastic. That would be a huge breakthrough. But this problem, this is basically one version of what we call LWE, like learning with errors. And this problem turned out to be very useful for many other applications. So that's what I'll tell you a bit about now. So questions so far? Going a bit fast. Yes. Good, thanks. So information theoretically, it's very easy. You only need to get. So again, it's a bit like in Ran's talk. Yeah, you get a linear number of points, and information theoretically, they uniquely determine the period of things. But it's really a computation equation. How do you figure out that period if you only, if you only have limited amount of time? Well, the best thing we can do is almost brute force, as I'll tell you in the next slide. More questions? Okay, so here's just the same one-dimensional problem, just a tiny bit more precisely. No, it's not lots of math. I think we'll manage. So the secret is this: there's a large integer number s. So this is the period. In my example, it was 5, but generally it will be a big number, like 2 to the power 100. And the the input you're getting are lots of samples that are sampled from the following distribution. Basically, you take ki, just a random integer, and you add a little bit of noise to it, ei. So it's think of ei as being some normal variable with some small deviation, maybe deviation of 1 over 1,000, 1 over n. And what you're getting is ki plus ei over s. So again, without the ei, if I just gave you ki over s, it would be exactly periodic, right? It would be either some multiple of 1 over s. But instead of giving you the multiple of 1 over s, I'm adding some noise. So it's a multiple of 1 over s plus a little bit of noise. Okay. And that's it. And your goal is to find s, find the period s. So it's a list. You're given a list of numbers between 0 and 1. That's all modulo 1. So yeah, so the precision is not an issue here. So you're given maybe some finite precision, maybe n bits of precision. Yeah. Second? The deviation of ei is, you can take it slightly sub-constant. Usually it will be 1 over polynomial, inverse polynomial in the security parameter. Yeah. So security parameter is log s. S is a big number, it's like 2 to the 100. Security parameter is like maybe 100 here. Yeah. So ei would be 1 over a million. Okay. Same.
So you get points which are not the range between ki minus 1 over s and ki plus 1. You get points which are far away.
No. So the ei is the numerator. So the noise is very small. Yeah, this is important. So if this like 100 over s here, and the next one is 101 over s, you get points in a very very narrow region around 100 over s. Yeah, that's crucial. So it's really, you're getting the multiple of 1 over s plus a little bit of noise. Yeah, it's crucial that ei is the numerator. Otherwise, it will be just complete mess and uniform, basically. So and your task is, as I was saying, is to find s. You can even think of a decision version. You can just distinguish this from uniform distribution. Can you tell me that those points have some kind of periodicity in them? It's not just uniform over the interval 0, 1. Even that seems hard. In fact, they're equivalent. The two versions are equivalent. And embarrassingly enough, the best known algorithm for this is basically brute force. You kind of try all possible s until one kind of matches. Once you have a guess, once you manage to guess the right value of s, you see that all the points align very nicely in multiples of 1 over s. But the only way to find this, as far as we know, is almost pretty much to try all possibilities. So it's basically exponential running time. We try, does it align with 1/5, with 1/6, with 1/7, with 1/8? Try all possible denominators until one of them gets a good match. And because information theoretically it's easy, there will be, once we find the right match, we'll know this is the answer. We'll know exactly that we found the answer.
So the number of points is only in log s?
So number of points, you pay for it in the running time. Ideally, you should be able to solve it with polynomial in log s, the security parameter. But if you want more, okay, I'm willing to give you anything less than exponential. And that's actually a very important point. I'll get back to it in the open questions. Because those points, yeah, but I'll get back to it later. More questions? So the gaps, you can look at gaps. The gaps are also multiples of 1 over s with noise. In fact, with a tiny bit more noise because you're getting noise from both ends. You can. I'm not sure how to use it, but try. It's in some sense, you're hoping to decrease the size of the magnitude of the numbers. Yeah, in a bit, this is a bit like how algorithms work, sieving algorithms. The trouble is you want to repeat that and get smaller and smaller gaps, but the noise blows up, so you can't do it too often. So I think your idea would be find 2 points that are kind of close together, subtract them, you get another point that's smaller in magnitude. Maybe that's what you thought, but maybe but the trouble is that you won't get a point here and a point here. S is so big so the example was misleading because I took S to be 5. But when S is like 2 to the power 100, you get maybe a point here, but you won't get anything here or here. The next point is going to be extremely far away. Yeah, thanks. Yeah, this is, if I could get points in consecutive, that would be fantastic. Yeah. But I don't have that. Okay, so this problem seems hard, and I should explain why we add a noise, because you're wondering, why did I bother with these EIs? Why won't I just give you multiples of 1 over S? Well, noise is absolutely crucial to this whole area. I mean, all of lattice-based crypto is based on noise, on this random perturbation. If you don't have any random perturbation, everything becomes easy. And let me demonstrate it here. If your input is really a multiple of 1 over S, so you're getting something like 100 over S, then it's easy. Then it's very easy to figure out S. In fact, you can do it with just one sample. You don't even need lots of points. So give me 1 point, I can tell you that that point is a multiple of 1 over S. I can tell you what the S is that that point is a multiple of. Does anyone know how? Have you ever seen that? Yeah, basically that's it. And this is, it's used in many other, in fact, it's used in Shor's algorithm. But here's the idea. So without noise, it's easy to solve LWE with just one sample. So here's the proof by Mathematica. I just took a number. Here's a number. Just one number, okay, between 0 and 1. And there's no noise added to it. So what I can do, I can look at the continuum fractions. I look at the convergence. And at some point, you just realize that the last number you get here basically gives you S. The denominator would give you S. So it has to show up, the number S has to show up in the continuum fraction, assuming that the numerator is coprime, and that happens with high probability. But that's basically it. So you can see the S in the continuum fractions. Now, what goes wrong when you add noise? Everything goes wrong. I mean, this algorithm is not stable, not robust, a little bit of noise, and you could think about this, but everything blows up during the continuum fractions. You add numbers, multiply them, you won't get anything meaningful. And that's why this problem seems hard. And the main result, the main hardness result shows that it's, and if you could solve LW, if you could solve this problem, you can solve lattice problems. Okay, and this is basically what I was telling you before. Basically, instead of getting an algorithm, right, we were trying to find a quantum algorithm for solving those lattice problems. We're still trying, but the algorithm failed, and the reason it failed because there was a missing component, and the missing component is LWE. So if you could solve LWE, then you can solve lattice problems. In other words, what you get is a reduction. You get a reduction that shows you that if you could solve LWE, you can also solve lattice problems. This is the theorem I'd like to mention a few words about, and then maybe tell you how it's used in applications, and including some of the recent stuff. More questions about this before I move on? Yes? No. So I'll tell you more about this later. So this is, I also mentioned a remark about this. And this is really important. This is really surprising and strange feature of bug in this theorem, that even if you solve LWE classic, I mean, LWE there's nothing quantum in LWE, right? LWE, I showed you, just a bunch of points and figure out what S is. Even if you solve it classically, you only get an efficient quantum algorithm for lattice problems. So I'll mention in a few slides why this is the case. Another way of thinking about this is that if you're willing to believe this kind of hypothesis about mathematics, about nature, that there's no efficient quantum algorithm for lattices, maybe it's like an axiom that you're willing to believe, then we get that LWE is hard. Okay, so the security assumption, if it says that there's no efficient quantum algorithm for lattices, then you get that LWE is hard. And yes. So yeah, I should have said, yeah. You have to assume that it's hard for quantum algorithms. Yeah, the assumption must be, maybe I misread this, but the assumption must be that there's no efficient quantum algorithm for lattices. Thanks. Yeah. Oh, that's what. Yeah, that would also imply LWE is hard even for quantum. That's true. Thanks. Okay. So I know what you're referring to as the next bullet. Yeah, but again, to summarize this again, we show that if you solve LWE, yeah, even quantumly, thanks, exactly, even quantumly, but also not quantumly, it shows that you can solve lattices using quantum algorithms. So you're the next shore, okay? So if you want to be the next shore, you have to solve LWE, or if you believe that there's no such way to solve, no way to solve quantumly lattice problems, you get LWE is hard, then you're a cryptographer, okay? So you can decide if you want to break it or use it. What's interesting here, I think, kind of philosophically, is that if you're like Gil Kalai and you don't believe in any quantum computers, they will never be built. I would claim that this theorem is still interesting because the theorem is not about quantum computers, about the physical reality. It's about a mathematical thing. The theorem tells you that if you make this, if you can one day prove, or maybe you believe that in this model of quantum computation, it might be completely hypothetical. Maybe it has nothing to do with nature, with physics. Maybe we even live in a completely classical world and we just think there's some quantum mechanics going on. Even then, even if you don't think there will ever be any quantum computers built, you still have to worry about the question of whether quantum algorithms can solve lattice problems, because that would determine if the theorem applies or not. So in other words, the theorem is not about quantum physics or quantum, it's about a model, a mathematical model of computation, and whether a certain problem is easy or hard in that model. Maybe putting it differently, imagine we really were living in a world that's classical. Maybe we didn't yet know about quantum physics and quantum computers. We would not be able to prove the theorem, even though the theorem is really about classical thing, about LWE being hard or not. It's not a question about anything quantum. So kind of knowing about this model of computation helps us say things about the entirely classical thing, like LWE. We don't have to have a quantum computer for that. Okay, so it has nothing to do with computers. It has to do with this model of computation. Okay, I hope this is not too confusing. Okay, so this is it. And going back to Krim's question, I should say that there have been attempts to kind of de-quantize it, to get rid of the quantum. Let me not go into that. Let me just say that it's not yet it's not fully de-quantized. I mean, it's not yet the full answer. You can do something without quantum, but for whatever reason, quantum is still essential in this theorem. So we don't yet know why it's there, but it's still there. More questions? Yeah, so we don't know if it's essential, and yeah, I hope so. Yeah, so it's completely, entirely possible this is just an artifact of the way we prove things. Yeah, and I would very much like this to be the case because it's annoying. You would like to prove it without the quantum, just directly to prove hardness. One thing I should say, maybe it's not necessary for the theory audience, but people might ask, why do you need the hardness proof? I mean, you already can just believe that LWE is hard. And the nice thing about the hardness proof like that is that it tells us something about the problem, how we should choose parameters. And going back to the question we had before about how much noise to add, the theorem, or the proof of the theorem, tells us how much noise to add. The theorem, again, the proof of the theorem tells us that if you add too little noise, then the proof breaks. So the proof needs a certain minimal amount of noise. And for many years, we didn't know why. I mean, there was some technical requirement. The proof said, for the proof to work, we needed a certain amount of noise here. And we didn't know why. But in 2011, Aurora and Gay showed that if you go below that amount of noise, if you reduce the noise below what's dictated by the proof, there are actually attacks. You can actually attack LWE, sub-exponential time attacks. So which was nice because it kind of, through a security proof, you could already preempt this attack. You knew the noise has to be at least a minimal amount, and it really matched perfectly what Aurora Gay showed like 6 years later. Okay. Question?
What about the other direction of the reduction? Is the WS special case of that?
Yeah, so
not really.
Yeah, so in a sense, you can, I mean, LWE, there are many ways of viewing it. You can view LWE as some kind of random average case lattice problem. Yeah, you can do it also the other direction. You have to be carefully with the parameters, but it's yeah. Okay. So maybe before I go on to the application, just a couple of slides on the question that was raised before. Why suddenly quantum? What's the connection to quantum? Again, LWE is entirely classical. It's just a classical question about points and periods. How come you suddenly end up with quantum? And the reason is that during that reduction, there is a certain task you have to perform, and I don't really know how to do it quantumly. So if you want to get rid of the quantum part, you should find a way to get around this issue. So I'm going to show you the issue that kind of forces quantum on this reduction. And I think it's interesting because I think this idea hasn't been explored enough. I can imagine other problems where the same idea might be useful. Basically, the kind of things you can do quantumly, you cannot do classically. And maybe one summary is that if you use quantum, you can create interesting quantum states and then take the quantum Fourier transform. So let me show you exactly what I mean. But I can imagine this idea also being applied to other problems. So maybe you'll find something here that connects to other things you know. It hasn't been used enough, I think. It's a well-known idea in quantum computation. And here's, I think, here's an example of why it's necessary here. So again, why quantum? So during the reduction, somewhere I'm going into the reduction, one part of the reduction. So don't expect to see the whole context, but at some point you end up with this thing. Okay, somehow you build this oracle, you build this machine, this algorithm that can do the following task. It's basically the same decryption task that I showed you earlier from Aitai and Warwick. So here's what you end up with. You end up with a machine that gets as input a point y, and the point y is guaranteed to be very close, within some distance d, so very close to lattice point, very close to some lattice point x. And what the machine can do, it can find x. So again, you have a machine that basically does this decryption. If you move a little bit away from the lattice, the machine can find back the nearest lattice point. Okay, so it's yeah, you can change the norm, but the distances are L2. We're in a few hundreds dimensions, and you have some lattice point x, and you have a point y that's very close to it. What this machine can do for you can find x. You give it y, and it finds x. Okay? So in many ways, this is a fantastic achievement because this seems like a hard computational task. The best known algorithms are exponential time for such a task. So getting this machine, getting this black box seems like a fantastic achievement. We finally have something that can find nearest lattice points. Okay, it actually solves something called BDD, or bounded distance decoding. But the problem is this. The problem is that you have this machine, you're very happy, but it seems totally useless, right? Because how do you actually use the machine to do something else? Something that's not exactly this task. Okay, you want to reduce, to solve something else using this machine. Just to connect this, LWE is in some sense a problem of that form, right? You get points that are close to the period, close to the lattice, and that's the connection here. So what do you do with this? What do you do with this machine, with this box? How do you do something useful with it? And the trouble is that to do something, the only way I can see, at least classically, the only way I can see to do something with this box is very stupid. So the only way I can see how to use it would be take some lattice point x, shift it a little bit, move it a little bit by not more than d, this distance d. You get a point y, and you apply this oracle or this machine with y. But that's very stupid, right? Because you get back x, and you already know x. So that sounds totally stupid, but that's the only way I can imagine using this machine. Because how else would I come up with a point that happens to be so close to the lattice? We're in high-dimensional space. It's mostly vacuum. It's all empty. If you choose random points, you'll never be close to the lattice. So if you want to be close to the lattice, how do you choose a point close to the lattice without already knowing what you're close to? So again, the only way I can see doing that is start with the lattice point, shift it by a little bit, and then you know what the nearest point is already. So it's not useful, right? If I start with x, move it by a little bit, get y, I call the box, I get x back, not very useful. This is some small distance. It changes in the reduction, so it depends on the reduction on the setup. It's a very small distance. The radius that you're allowed to move the point depends on the geometry of the lattice. Yeah, it's a small distance. Exactly. Exactly. So why? So this thing that sounds absolutely obvious classically turns out that quantumly these things are very useful. Quantumly, being able to compute something you already know is extremely useful. So that's kind of the surprising thing. That's what quantum computers are very good at doing, computing things they already know, like factoring 15 into 5 and 3. but here's a more serious example. So quantumly, the fact you can compute x from y, you can recover x, means that this transformation that maps x into y, that becomes a reversible transformation. And quantumly, everything has to be reversible. And therefore, changing a memory register from x into y is something you normally cannot do. You cannot take x and replace it by y, because that's not a reversible transformation. But if you can compute x back from y, then suddenly this becomes reversible. You can take x and map it to y, and it still go backwards, so the thing becomes reversible. Why is that good? Why is it so good? Because now once you can do things reversibly, you can create quantum states, you can do interesting things with it. Namely, you can create this, what we call this periodic Gaussian state. So it's a state on the lattice. It has this period. But the only way to create this state is by being able to kind of erase or uncompute the lattice point x. Okay, so I won't give many more details on this. Let me just summarize that computing things you already know, classically, it's often not very useful. Quantumly, it's useful. It allows you to create quantum states. And once you create the quantum states, what you usually do in quantum, almost always, you take the quantum Fourier transform. And turns out this basically gives you short vectors in the lattice through the quantum Fourier transform. So again, this is really like a one-minute summary of this line of work. Don't expect you to see all the details, but just remember this idea. I think it can be used also elsewhere, maybe coding problems, graph problem, I don't know, but this idea of like planted, if we have a planted problem, this might be useful. So planted click, so you know, those things might come up there too. I don't know how to use it in those other contexts. Just an open question to think about later. So that's kind of it for LWE questions, or for the background on LWE. I'll tell you some applications now. Questions? Okay, so a bit about, that's okay, it's not broken. It's intentional to wake you up. Applications. So LWE in the last decade or so became very useful in crypto. There seem to be lots of applications of it. It's basically you can do almost anything with it. Any cryptographic protocol that you wish, you can do using LWE. So it's amazingly versatile. It's, as we said, it's provably secure. Provably secure as lattice problems. So it's as hard as lattice problems. It's still believed to be secure against quantum computers. At least it seems to be the case. And also quite efficient. Actually, some of the recent proposals seem to be kind of on par with things like cars, say. So those things are actually being standardized nowadays. Like NIST is trying to standardize. The National Institute of Standards and Technology trying to get standards for post-quantum crypto, and lattice-based crypto systems are one of the leading contender for this. So list of applications in crypto is very long. Probably don't know the definitions of half of those protocols, but those are really important things apparently in crypto. Just the most recent one, one of the most recent applications is to get NISIX for NP. This is a result from Pikert and Sheehan. There are lots of other things you can do with it. Basically, it seems like the nice thing about LWE is very flexible. You see, the definition is very simple. The definition of the problem is very simple. You can do lots of things with it. It's very natural to use it, and you can do lots of things with it. Um, I want to show another application to connect this to machine learning. As I was saying, everyone nowadays has to do machine learning. But before we do that, maybe just to show you how this crypto is used, because you might be tempted to, you might be thinking it's very hard. This crypto-based, lattice-based crypto is very hard. Actually, I want to show it's very simple, despite what this cartoon shows. It's actually all very, very simple. So I'll just demonstrate how to encrypt, how to do public key encryption kind of live. So this is something you could do, I imagine, like high school students, if you wish. And here is the simplest LWE-based public key crypto system. It's almost rigorous, it's almost fully precise. I'm hiding a couple of things, but here's the idea. So, so I'll take a volunteer, maybe any volunteers, maybe Yuval. You will, okay. So I'd like Yuval to send me a message, and you can all listen. And you'll have to guess, you're the eavesdropper trying to see what Yuval sent me. I'll know what he sends me because I have the private key. So the private key is a random odd integer, S. It's in my head, I'm not telling you what it is. Okay, so it's a random odd integer. And what I'll send everyone, my public key, I'll just send a list of random multiples of S. So, 10S, 15 times S. But I'm going to add a small, even random number. So this randomness shows up again. So here are the numbers. There'll be more than them, but imagine only 5 numbers now. And all those numbers are multiples of S plus a small even number. So this, and maybe there are a few more, but I only listed 5 now. So again, my public key are just multiples of this number S plus a small even number. Okay, so far so good. Okay, and now how do you encrypt? So Yuval wants to send me either 0, 1. Imagine it's just a yes/no message. So he chooses a subset of those numbers. So he has to choose a subset of those numbers and basically add them up, add the numbers up. Okay, so maybe he chooses, this, and this. Randomly chooses one of the 2 to the whatever 5 possible numbers, adds them up, and just adds B. So if he wants to send me 0, doesn't add anything. If he wants to send me 1, he has to add 1. Okay? So your task is to choose a subset of numbers and add your secret to it, your message to it. Sorry, your message B to it. What's your? You want a piece of paper to add? You not the empty subset. So, yeah. Yes? 289? 298. Okay. So we never met before, right? The messages is 1, right? So I think you already broke it. How did you decrypt the message? Yeah. So good. So Nati broke the system live without a quantum computer. Terrible. At least you should have used a quantum computer. Yeah. So what's going on here? The idea is this. Here's my secret. My secret was 1001, and I chose a simple number. I didn't expect Nati to see that, but I chose a simple number. I chose 1001, so it's easy to see how the numbers work out. And as Nati observed, all those numbers are of the form, it's a multiple of 1001. This is 98 times 1001 plus 2. And this is 65 times 1001 plus 8. Okay, and so on and so forth. So all these numbers are multiple of 1001 plus an even number. So how do I decrypt? Now, I got this message from Yuval. I know the secret. I know S. I know 1000. I know it's a multiple of 1001 plus an even number because he just added up some of those numbers. All of those numbers are a multiple of 1001 plus even. So if you add them up, you still have a multiple of 1001 plus even. So I know that this is a multiple of 1001 plus even, or plus odd, depending on the message B. So if the message B is 1, that will be actually a multiple of 1001 plus an odd number. And if the message is 0, that would be a multiple of 1001 plus an even number. So how do I decrypt? Basically, I divide by 1001. I take the remainder under division by s, and the remainder is 9. It's an odd number, which shows me that the message must have been a 1. Okay? Because if the message were 0, it would have to be a multiple of 1001 plus even, not plus odd. Maybe Israeli high school student, yeah. Okay. But I think it might be doable if you if you do it slowly enough. Yeah, I think it doesn't require exponentiation or modular arithmetic. It's all in integers, so maybe it's doable. Try. I haven't tried it, admittedly. Maybe I should try this year. Okay, so I hope this was clear. This is very simplified. There are a couple of things I'm hiding here. Yes. So why did several numbers? Well, if I only give you one, you would have to choose this number, basically. So I want to make sure there are enough possible messages. But I think what I should really be saying here, and thanks for pointing it out, I really should explain why is this hard. How do you prove security of this? And the reason you can prove security is basically based on the LWE problem. What you can show that these numbers are basically look uniform to you. Well, not to Nati. For most people, they would look uniform. And the reason they look uniform is because there are multiples of a secret thing, like here, plus a little bit of noise. And basically what LWE shows you or tells you is that if you have a periodic signal and you add a little bit of noise, you can't tell what the period is. It hides the period. And that's what we're using here. So the security proof, I'm not going to do it here, but the security proof shows that these numbers are basically uniform. And to complete the proof, you have to say that when the numbers are uniform, then the message has no information. That's why you need several numbers. If you only had one number, the message really reveals, the ciphertext reveals the message, if you only had one number here. No, because it has to be, so it has to be like a security parameter, because the number of possible subset that you've all had to choose from has to be exponential in security. Yeah, so it would typically be like 100. Now, maybe it looks very inefficient because you need like 100 numbers. Those numbers are big, but actually you can make those things very efficient. What I'm showing you here is a very simplified version of it. Okay, so again, black, something completely different. I want to switch to more recent work from the last few months on machine learning, just so I can also claim I'm doing some machine learning. But in fact, LWE, I mean, the L in LWE is learning, so there was some connection to machine learning, but it's not convincing enough, I think. I mean, I should also mention deep learning to be more convincing. But it's in some sense, yeah, LWE is a hard learning problem, so it's already there. A much more impressive result was shown by Klivens and Sherstov in 2006. They showed that if you assume LWE, you also get hardness of learning intersections of half spaces. So that gets closer to, I think it's an interesting learning problem. What I want to show you about, tell you about today is something else. It's about adversarial examples. That's a paper that started, this area started in 2013. A few people from Quran, from my department, and others. This is not Mario Szegedi for the theory community. There are lots of Szegedis in Hungary, and this is a different Szegedi. It's Christian Szegedi. And so what you see here, sorry, I only found a picture of a pig. So those are pigs. But can you spot the differences between the two pigs? Do you see a difference? One is adversarial. Which one is adversarial? Thank you. Yeah, one is adversarial, and the one on the right is adversarial. So those are not the same pigs. This is the original happy pig, and someone added a tiny bit of noise, like 0.005 noise, and got the other pig. They look absolutely identical, but if you use the deep learning network, it will tell you that this was a pig, the other one is the airliner. Just to fit with when pigs fly, it will be airliner, right? Yeah, so why is that so? Well, that's something you can read in the paper. That's trying to understand those networks are very sensitive to this noise, and by taking the gradient of the input of the network, you can come up with those very tiny deviations that make it think that a pig is an airliner. Of course, this can be a serious issue if you use this for like mission critical systems and not for identifying pigs. But this was the whole area, and thousands of papers on this, which probably doesn't mean much in machine learning, but there are lots of papers on it. And there's a nice recent work of Bubeck, Price, and Rosenstein. They were trying to get some more theoretical aspects on this. And they gave an interesting example where robust classification is information theoretically possible, but computationally intractable. So what is robust? Robust means that even if you change a bit the input, it's still pig and not an airliner. Okay, so you can make it precise. I won't try to do that here. So again, they have this example. I'll show you the example now. And this is even though non-robust classification is super easy. So like here's the example. I'll explain again what I mean. And I'd have to connect my laptop. Take a second to load. So basically, they show an example. And they show that this example, there are two distributions they're trying to distinguish. Two distributions in high-dimensional space. And here is what it looks like. There are red points, there are blue points. And you're trying to distinguish them. Can you distinguish them? Can you see the pattern? You probably can't. Nati, can you see that? Okay. Nati cannot see the pattern. It's not there. So there's a pattern, actually. And I have to rotate a bit so you can see it, because now you don't see anything. But if I slowly rotate, you see there is a pattern, a very strong pattern, but not showing up yet. And slowly getting there. Okay. Maybe you can start seeing something here. Okay. That was their idea. Their idea was that there be a certain direction where the points are on this interleaving hyperplanes. So all the red points are in the odd positions and all the blue points are the even positions. That was their idea. The direction is secret and all other directions are just Gaussian. So it's all just normal, standard normal, except in one special direction which you don't know. And your task is to learn this. So you get points, you get lots of samples from maybe labeled, some are blue, some are red, trying to tell which one is which. Okay? And trying to do it robustly, such even if you move a little bit the coordinates, you won't be able to tell this apart. Okay? So this is, again, if I move it a little bit, you won't see anything. And going back here, so what they showed is that they have this task of blue versus red, and they show that information theoretically, it's actually easy. Just like Elkan asked before, if you get a small number of points, information theoretically should be able to tell, should identify this direction, the secret direction. But computationally, it seems intractable. I'll tell you more about this later. But yet, they said if you train normal deep learning network, it will classify it, but in a non-robust way, very easily, just like the pig was identified non-robustly. And to get this last point here, this is really a hack. I mean, basically what they did, they provided the color. They provide the network with the color also. A network can use the color to identify if it's a blue or red. It sounds very stupid, but it's not robust because blue and red are very close together in some sense. So you encode the color in the input and let the network basically use the color as the way to distinguish the two sets of points. But the colors are very close together. So you choose maybe blue and light blue. Okay. So the network can use the color, but it's not robust because if I slightly change the color, the network would suddenly think it's the other. This is completely the other class. Okay. So that was their idea. And let me say it again because it's very confusing. They said we'll encode this input in a way that's kind of inherently easy, kind of trivially easy to distinguish based on color. But the colors are so close together that it's not robust. And if you want to be robust, you really have to work hard and identify the direction. So they said this is something that happens often, that deep learning or neural networks, they would pick on some totally useless or irrelevant feature, but that helps them to distinguish the two classes. So I'm running out of time, so let me just say this is basically distribution you get in this hidden direction. What do I mean by intractable? So what they could show, the only thing they could show is that it's hard in what's known as the SQ model. I won't define here. It says that if you only look at averages, you won't be able to find the hidden direction. That's basically what it says, only looking at averages. It's a very restricted model, and yet it captures almost all the known algorithms. So I think it's a very interesting statement, but you would really like to get a more meaningful hardness proof. And what we show and observe is that this problem is computationally hard, as you might have guessed by now. If you can solve it, you get an efficient quantum algorithm for lattice problems. So this problem you saw here might have looked familiar. Indeed, it is familiar. It has lots in common with LWE. So this problem is basically some variant of LWE, and you can prove that it's hard by following the LWE hardness proof, the original one from 2005. Say it? So the problem, either find a direction or distinguishing from a standard Gaussian that has no hidden direction. Yeah, either way is fine. Yeah. Basically, this distribution is kind of pseudo-random. It looks like a Gaussian. So the connection to adversarial examples is that if you want to learn this properly, you have to be able to support a small distance, and those hyperplanes are separated by a small distance. So there is distance between the blue and the red. It's a small distance. And information theoretically, you can do that, because even if I move the blue point a bit, it will still be far from the red plane. But computation, it seems it's intractable. No, so this problem is it's not yet the problem it's not the problem that would show up in practice. Of course, it's not the problem that would, but it's I think the closest you have so far for something demonstrating the difficulty of robust learning. No, spheres you could not. It's really about direction. You can, because spheres you can compute the norm, so it's not really. It's really about direction. You can try other patterns, but we don't know actually. It's quite fragile. One of the open questions is to figure out what happens if it's maybe not equally spaced. Just change the spacing a bit. In some cases, you have faster algorithms. If the moments don't match, you can see that. But some other cases, if the moments match, we don't know. We have no hardness proof nor algorithms. Yes.
This particular case was important to use L2 law, but there are also the same examples in L0 law, which are when you allow small number of pixels to change, but by a lot. Because then you'll not be able to pay your flick of light blue versus blue. Every average of random subset will still be significantly different between the light blue and blue. So it's essential to use only particular distance functions.
Yeah, so this is quite fragile, this example. But we were lucky that this came up independently. But I think there are interesting questions here. But we should probably wrap up. So maybe I'll skip the open questions and just yeah. Yeah, I can ask you. Okay, I can ask it later. Offline. Okay. A question? Yeah, so I didn't talk about the applied, but I think Google Chrome had an experiment once. It worked. But now the main effort is to make it the standard so everyone can use it. And this is what NIST is trying to do, the Institute of Standards. There's a competition. People are trying various parameter settings, and they're trying to get a standard ready. So you have to use it this parameter, this dimension, and so on. Something that everyone can now use, just like RSA. Everyone knows what the parameters are like, how to implement it.
Yes, I think I could apply it.